When I was a grad student at the University of Florida, I can remember a conversation with my advisor, Dr. James Hunter, that had a tremendous impact on me, both at the time and as my career progressed. We were having our weekly meeting where I updated him on the work I had been doing and we discussed possible paths forward. The specific topic we were chewing over had to do with my attempt to not only include gas and dust in my simulations of various galaxies, but also with the idea that maybe we could get the simulation to allow for star formation and death to see if that helped form the spiral structure I was trying to reproduce in my models. As the conversation progressed, Dr. Hunter made the point that if we were going to do things right, we probably should know a little something about the latest work about what is known as the stellar formation distribution function, which is a fancy way of saying when a giant molecular cloud has a region that undergoes collapse and star formation, what is the distribution of masses those formed stars have? Are they mostly big and massive stars with only a few orange and red low-mass stars? Or was it the case that the high-mass stars were the outliers and there were lots and lots of the low-mass stars being formed? The answer to this question would affect the model pretty significantly. So off I went, and I tried to run down the answer to the question, and what I found was there really wasn't actually a good answer. We just really didn't have a good sense of how to really get at that. When I brought this up to Hunter, he didn't seem surprised. Instead, he talked about the bias in astronomy towards objects that gave off a lot of energy in the visible part of the spectrum. What he pointed out was that, for a long time, astronomy had built models on what it saw, and of course, what you tend to see when you look out into the sky are the really bright things. This is something that he called the Lighthouse Fallacy. If you imagine that you're a ship sailing at night several miles offshore, you can easily see the lighthouses that have been erected as navigational aids. They're bright and put in places where they stand out. If you were to build a model of how people on shore lived based on those observations alone, you'd end up concluding that the coastline was sparsely populated by people who all lived in tall cylindrical buildings. Not quite exactly what's really going on. However, if you were to use some other method of seeing better, say a pair of binoculars or a spotting scope, you would realize that there were a lot of dimmer lights that you had missed when you looked only with your naked eye. Without this additional help, you'd miss a lot of the smaller dwellings. Even more difficult, however, is the idea that there might be dwellings or businesses that aren't lit at night for some reason or another, and so you'd miss those altogether. This idea was revelatory for me because it was, in a sense, my first recognition on a personal level that what we see really does bias us quite a bit. If all you do is look up, all you really are going to see are the big bright stars, at least if what you're looking up with is basically your naked eye. If you use a telescope, you very quickly begin to see those dimmer K and M stars, and you find that they outnumber the bright O and B stars something like 10,000 to 1. The question that a lot of researchers at the time were trying to answer was whether this ratio kind of reflected the abundance of stars when they formed. Since the O and B stars are more massive, they fuse their hydrogen at a much higher rate and thus have much shorter lifetimes. And so maybe they were born at roughly the same rate as their lower mass companions, but since they died so much earlier, we didn't see as many of them later on. It wasn't until the advent of both really high-quality ground-based telescopes situated at high altitudes that could make observations in the infrared part of the spectrum that we finally began to make some serious headway on the stellar distribution problem, as these scopes could look further into star-forming regions of giant molecular clouds and make some counts as to what was actually being created there. This work is actually now being refined and extended by the European Space Agency's Gaia mission. Unfortunately for me, we never did really get a good handle on how to work star formation into the models before I finished up my PhD work. Nevertheless, what I realized is that the Lighthouse Fallacy is something that astronomy has had to contend with for a long time. But for almost all of our history, the progression has been in trying to either see the faint things better or to look in different wavelengths of light that don't make it to the surface of the Earth due to being blocked by the planet's atmosphere. Until the 1970s, almost no one thought that there might be stuff that we can't see, no matter how hard we look. That was until one of George Gamow's students, Vera Rubin, decided to take on what seemed like would be a fairly simple research project and came up with results that surprised an awful lot of people. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 3, Finding Our Place. Episode 48, Matters, Dark and Mysterious. Vera Rubin was born Vera Florence Cooper in Philadelphia, Pennsylvania on July 23, 1928, to Jewish immigrants who had met while working at Bell Labs. When Vera was 10, the family moved to Washington, D.C., and during her high school years, she and her father, like so many others we've discussed, built a small telescope. Her imagination fired by viewing the skies, she chose to attend the all-women's Vassar College because she admired its most famous member of the faculty, Maria Mitchell. Earning her bachelor's degree in astronomy at the age of 20 in 1948, she set her sights on graduate school, but found that she was barred from her first choice, Princeton, due to her gender. Instead, she enrolled at Cornell, where she studied under Hans Bethe and Richard Feynman and did research in galactic dynamics. This research proved to be fairly controversial, and she was forced to overcome a tremendous amount of bias even to present it. Nevertheless, she earned her master's degree in 1951 and moved back to Washington, D.C. to enroll at Georgetown University, the only institution in the U.S. Capitol to offer a program in astrophysics. It was at Georgetown that Rubin began to study under George Gamow, who had recently left the University of Colorado. The results of her observations of galactic motion showed that galaxies were not evenly distributed throughout space, but rather were clumped or grouped together into clusters. As was the case for their master's research, this ran counter to the prevailing view in 1954, and so it created a good bit of controversy among the astronomical community. Following the award of her PhD, Rubin held a number of positions in academia in the Washington, D.C. area. In 1963, while an assistant professor at Georgetown, Rubin worked with George and Margaret Burbidge, who we've discussed in a previous episode, to make observations of the motions of stars within individual galaxies using the 82-inch reflector at Texas's McDonald Observatory. This work would be continued 2 years later at the Palomar Observatory, where she became the first woman to make observations at that telescope. In 1965, Rubin took a position at the Carnegie Institute as a staff researcher in the Department of Terrestrial Magnetism, a somewhat odd place for an astronomer to end up. It was there she would meet her longtime collaborator, Ken Ford, who was one of the best instrument makers in the United States at the time. The two would collaborate to make further observations to support Rubin's thesis that galaxies were not evenly distributed, something that continued to create a lot of controversy. In the early 1970s, looking for a respite from the back and forth related to her clustering research, Rubin decided to return to a topic she thought would be less contentious: the work she had done with the Burbidges on observing the motions of stars and giant molecular clouds in nearby spiral systems. The idea that she had was to measure the velocities of giant molecular clouds, these giant, huge, sort of gravitationally held together clumps of hydrogen gas sprinkled with dust and that sort of thing, that were moving around the centers of spirals, and by doing so, coming up with what's known as a rotation plot or a rotation curve for the galaxies as a way of understanding how the mass of the galaxy was distributed. So before I go any further, let me see if I can explain how this all works. And the best way to do that, I think, is by starting with something that we've already talked about, and that is thinking about the motion of the planets in our solar system. We know that the planets go around the sun with periods, or, amounts of time, that obey Kepler's third law of planetary motion for the most part. This law says that the square of the time it takes for the planet to go around the sun is proportional to the cube of the planet's distance from the sun. When you plot the period, as that first quantity is called, against the distance, you get a very specific type of a curve that follows a very specific mathematical function. Now, you can also look at this another way, which is to say that when a planet orbits the sun, it has to go at a certain speed to remain in its mostly circular orbit. If it goes too fast, it flies off into space, and if it goes too slow, it would fall either towards or actually into the sun on a curving path. Thus, you can do a little bit of algebra to determine the velocities of each planet, and then plot those against the distance, and you get a very identifiable curve on the graph. We'll put a picture of this curve on our website for the podcast, thescientificodyssey.typepad.com. Newton, of course, with his universal law of gravitation, showed that the reason you get these results has to do with the fact that the sun contains about 99.8% of the mass of the solar system, and so Kepler's relationships fall out of Newton's three laws of motion and that universal law when applied to a system with that large centrally gravitating mass. We can see similar results when we look at the orbits of the mini-moons of Jupiter around it, or with the rings of Saturn. Alright, so far so good. When we look at a spiral galaxy and we count the stars, what we see is that most of the mass is found in the form of stars, with some of the mass being found in gas and dust. But the thing that's interesting is that mass isn't all at the very center of the galaxy. It's spread out across that disk, and so the calculating of the gravitational pull of all of that mass on a star that's orbiting the center of the galaxy, or maybe a giant molecular cloud that's orbiting the center of that galaxy, can be a bit trickier. Fortunately, you can show using some calculus that if you have a star or a giant molecular cloud that's orbiting, say, a third of the way out from the center towards the edge, you only have to count the mass on the inside of the orbit to determine how fast the star would have to go to remain in that mostly circular orbit. And of course, the same is true for those giant molecular clouds that are made of hydrogen and helium gas. Conversely, and this is going to be important, if you know how fast the star or cloud is going by observing its speed using its Doppler shifted spectrum, you can reverse the calculation and figure out how much mass there is inside of the orbit to produce enough of a gravitational force on the star or on the giant molecular cloud to hold it in that orbit. Now, when we do this for our solar system, we see that for the planets, the further away they are from the sun, the weaker the gravitational force the sun's mass exerts on the planet, and so the slower the planet has to go to remain in its orbit. Venus moves more slowly than Mercury. The Earth moves more slowly than Venus, and so on until you get out to something like Pluto, and beyond that even, where the speeds are just a mere fraction of their innermost worlds. Galaxies, on the other hand, don't actually work that way, again, because most of their mass is not actually concentrated at their centers. As you get further away, there is more and more mass inside of the star's orbit, and so the net gravitational pull of that mass on the star gets bigger, and so the star has to move faster to remain in that mostly circular path around the galaxy's center. In other words, a star that is 15% of the way out from the center of the galaxy towards the edge of the galactic disk has to move almost twice as fast as a star that's maybe only 7.5% of that distance. Now, if a spiral galaxy were a uniform disk with the same density of stars from center to edge, this trend would continue all the way out to that edge, and the stars near the edge would have to go a whole lot faster than the stars near the center to maintain circular orbits. However, when we look at the starlight we receive from a spiral galaxy, what we see is that the density falls off according to an exponential function, meaning that a typical spiral galaxy is fairly dense near its center, and then there are fewer and fewer stars, maybe say per cubic parsec, as you get further out towards the edge of the galaxy. A way to imagine this is to think of the population density of a major urban area. Since I live near Atlanta, Georgia, I'll use that. Down near the city center, there are a lot of people living close together in apartments or in houses with very small yards. However, as you move away from that center, you find that the population density begins to drop as there are fewer apartment complexes and the houses start to spread out. Once you get out to the suburbs and exurbs, the density may be less than half of what it was in the center of the city, and by the time you get out to where I live, in a small rural town very far from the center, the population density is a fraction of what it was downtown. You can kind of think of galaxies in the same way, or at least spiral galaxies. So, if you look at the light we get from the stars that make up the galaxy, you can get a pretty good idea of where the mass is and how it's distributed. Once you do that, you can calculate what the rotation or velocity curve for the galaxy should be. In other words, how fast the star would have to move to be in a mostly circular orbit given the starlight and the mass that you think produces it and how it's distributed through the galaxy. When you do that, the answer you get, you think you're supposed to get anyway, is that the velocity rises linearly as you move away from the center of the galaxy until you get about a quarter of the way out towards the edge. From that point, the needed rate of motion turns over and begins to drop until, out near the edge of the galaxy where almost all of the galaxy's mass is inside a star or giant molecular cloud's orbit, that rotation curve that describes the speed that the object has to have in orbit becomes Keplerian. In other words, it looks a lot like what you would see in the solar system. And so that's what Rubin was working on. She had decided to continue the work she had done nearly a decade earlier, and so she wanted to carefully measure the velocities of the stars, and more importantly, the giant molecular clouds of the Andromeda Galaxy, in order to get a second way of characterizing how the mass in the galaxy was distributed and how much of it there was. Now, to be clear, this is another one of those things where there are a lot of details that you have to get right to come up with a reliable answer. And so the process of getting the data and analyzing it, reducing it down to something, took quite a while. However, when Rubin had finished her observations and number crunching, she came to one really inescapable conclusion. Something was really, really off. What she found was that instead of the rotation curve turning over and then decreasing in value after you got about a quarter of a way out from the center towards the edge, that rotation curve actually went more or less flat. What that meant was that when she did the calculations, there had to be more mass affecting the orbits of the stars and gas clouds than could be accounted for by looking at the light coming from the galaxy. In other words, there seemed to be matter no one could see. How much matter? By her early calculations, it was going to be at least 5 to 10 times as much, and later on, that number would become as big as 50. Having hoped to leave the controversy behind and spend a bit of time doing what should have been a nuts and bolts astrophysics project, Rubin had landed in the middle of another great conundrum. With Rubin's discovery of a whole bunch of missing matter in the Andromeda Galaxy in around 1972, there were two responses from the astronomical community, both scientifically appropriate. The first was to see if the Andromeda Galaxy was a special case, and the second was to find out if there were any other observations of the motion of other types of astronomical objects that showed that there might not be enough mass to account for that motion. In the first effort, over the next few years, Rubin and others got to observe the rotation curves of as many spirals as they could. In nearly every case, they were able to find very similar results to what they had seen in the Andromeda Galaxy. Missing matter seemed to be everywhere they looked and in roughly similar proportions to what they had found there. In the second effort, it turned out that some 35 years earlier, another astronomer had made observations of galactic motions and had come to similar conclusions. He had even given the missing matter a name: dark matter. The idea of missing matter had actually been sort of lurking around the edges of astronomy for quite some time. The earliest paper that seems to mention it is from a talk given by Lord Kelvin in 1884 regarding the speed of stars orbiting the center of the Milky Way galaxy. Kelvin noticed that the stars seemed to be moving too fast for the mass that was visible at the time. He suggested that there might be many stars that were quote-unquote dark bodies that we couldn't really see. Henri Poincaré made similar observations in 1906, and Jacobus Kapteyn refined these observations in 1922. Finally, in 1932, Jan Oort suggested that unseen matter might be responsible for the observations of stellar motions that he was making. However, the first really scientifically solid piece of work was done in 1933, just a year after Oort's publication, by a man by the name of Fritz Sawicki. Zwicky was something of an iconoclast. He had been born in 1898 in Bulgaria to a wealthy and influential family of Swiss and Czech origin, and at the age of 6 had been sent back to Switzerland to live with his grandparents and study commerce. As such, he was spared the brutality of the Austro-Hungarian side of the First World War and was able to pursue an education. Counter to his family's wishes, however, he did not pursue a career in business, but instead found himself attracted to the sciences, where his mathematical talent could be employed with great effect. He attended college at what was then the Swiss Federal Polytechnic, now ETH Zurich, earning his PhD. And in 1925, he received a Rockefeller Fellowship and immigrated to the United States to take a position at Caltech working with the newly recruited Robert Millikan. He would remain there for the rest of his career. Before we get into the part of the narrative about his research that led to his proposing dark matter, allow me to make a couple of other comments about his contributions so you get a better sense of who the guy was. He was among the first to put forward the idea of neutron stars while working with Robert Oppenheimer, and he actually coined the term supernova. During and after World War II, he worked on jet propulsion, developing some of the earliest jet engines, and he had over 50 patents in his name for the technologies that he developed that were associated with those projects. In his brief biographical sketch of Zwicky, author Stephen Maurer notes that a number of conversations in astronomy and astrophysics, in later years started with, quote, Zwicky noticed this problem back in the 1930s. Back then, nobody listened, end quote. This may be why Zwicky, over time, gained the reputation of being sort of a good-natured curmudgeon who was profoundly generous and charitable throughout his life, but who didn't suffer fools lightly. Thus, he had no problem suggesting a lot of out-of-the-box thinking when it came to solving problems and being really, really critical of his colleagues when they weren't as accepting of those ideas as he thought they should be. The problem he was trying to solve in 1933 had to do with the motions of galaxies in clusters, specifically the cluster known as the Coma cluster. When we look at how a galaxy moves, there are two pieces we have to take into account. The first of these is sort of the motion that's due to the overall expansion of space-time that sort of drags everything along with it. It's that idea that we talked about earlier. When you blow up a balloon, all of the dots that you might have drawn on the balloon just get dragged further and further apart as the balloon expands. The second is the local motion of a galaxy with respect to the galaxies around it. Now, this motion is caused by local gravitational effects, the mass of one galaxy pulling on the mass of another galaxy, and those two things sort of affecting each other. If the only thing that were taking place were that first sort of expansionary thing, all the galaxies would be moving away from all other galaxies. However, if you were able to subtract that out, you can get an idea of the overall mass of two galaxies by how they cause each other to move. For example, the Andromeda Galaxy and the Milky Way Galaxy, our own galaxy, are moving towards each other at a rate of about 400,000 kilometers per hour, due to the fact that the mass of each galaxy is creating a gravitational attraction between the two. While this may seem like an enormous speed, the distance of 2.5 million light years that separates the two galaxies means that it'll be something like another 400 billion years, or it's not 400, 4 billion years before a collision actually takes place. So you don't really have to hold your breath on that, right? What Zwicky actually did was to look at the motions of the galaxies in the Coma cluster to see how much velocity they had compared to how much mass he could actually see by looking at the light coming from the galaxies in the cluster. Again, this is like the idea we brought up earlier when we said that a planet had to have the right amount of velocity to stay in orbit around the sun. The same thing goes for the galaxies in a cluster of galaxies. You can't have too much velocity or the galaxy would have flown right out of the cluster a very long time ago. And if you have too little velocity, then you merge with another galaxy. So, what did Zwicky find when he did his research? When he counted up his velocities, and then he took a look at how much matter there had to be according to the light from the stars? Well, you probably guessed it. He's got too much velocity, or conversely, not enough mass. What he saw was that the galaxies on the outer edge of the cluster were moving way too fast to be bound to the cluster, given the amount of mass that could be seen in the visible part of the spectrum for all of the stars contained in all of the galaxies of the cluster. And he had to make some estimates to do that. But when he did that, his calculations showed that there had to be at least 160 times more mass in the cluster than what was being seen. Now, it turns out that that number is too high by a factor of about 3 due to the fact that the Hubble constant at the time wasn't very well known, and so it was too big. But the work was a clear indication of a really real thing. In other words, there really wasn't enough mass to cause the motion that was being seen. Because of this, Zwicky said that there was some missing mass, something he called Dunkelmaterie, or dark matter. Unfortunately, as the anecdote goes, nobody listened. At the time, there were a variety of possible explanations made as to what would account for the higher than expected velocities, some of which, by the way, we'll return to shortly. These included there being types of objects that were too faint to see, that there were contributions from gas and dust which didn't put off a lot of light, or there were other forms of mass besides stars. These explanations, combined with the fact that Zwicky often rubbed people the wrong way when he criticized their work for being subpar, led to no one really following up and the paper falling into obscurity, at least until Rubin's work appeared in 1972. As one final note about Zwicky's work that will be important for us here in a bit, he was also the first astrophysicist to suggest the phenomenon known as gravitational lensing. So, what is this? Well, the idea is something he built off of, based on Einstein's original prediction that a massive object like the sun could bend the light coming from a more distant object due to the effect it has on warping spacetime. What Zwicky was able to show was that galaxies should be able to do the same thing if there was a light source further away from the observer than the galaxy was, and that the mass of that galaxy would sort of have a way of focusing or brightening that light in certain very specific characteristic ways. And that this would allow for another way to determine the mass of the matter that made up the galaxy that was in between the observer and the bright object trying to be observed. Now, this wouldn't actually be observed until 1979, but it's actually become a common technique and has been used to verify the existence of black holes, among a number of other things. So, by 1980, there was a real problem in astronomy. There seemed to be a lot more matter in the universe than was being seen, and there was no way to really get around this. Too many observations had been made of too many different types to suggest that this was some sort of observational error or instrumental artifact. The question was, then, how do we explain the observations? Well, to do this, there are 3 options. First, you can do what the astronomers did after Zwicky's original announcement, and that is to say that there's a whole lot of matter that we actually aren't seeing. In this case, the matter is dark because it doesn't really put off a lot of light, or that the light that it does give off is mostly absorbed by gas and dust between us and it, or maybe by our own atmosphere. Second, you can say that there's a problem with our theories about how gravitation works. The idea here is that maybe general relativity has a flaw that really only manifests on a galactic scale. This would be sort of a similar kind of thing to how general relativity replaced Newtonian gravity when the latter failed in the extreme case of explaining Mercury's motion very close to the Sun. The third thing that you can do is that you could say that there's a type or a set of types of matter that do not behave in the way that regular old everyday matter, at least the type of matter we experience in a sort of everyday kind of way, doesn't act the same way that matter does. The matter is dark in this case because it doesn't interact either with itself or with other matter through either the electromagnetic or weak interactions, and so doesn't absorb or produce light. This odd new form of matter would only be detectable through its gravitational interaction. So let's examine each of these possible explanations in light of the observations made over the last 40 years and see where that gets us. Now, obviously, the best case scenario would be to find the missing mass in normal matter that we just aren't seeing. So, if we go looking for that, what could it be? Well, the first thing you can think about is that you could have some really simple stuff like free electrons and ionized nuclei. Those won't absorb or produce light because they don't have energy level transitions. Another thing might be diffuse hydrogen spread out between the stars and, more importantly, in between the galaxies themselves that wouldn't produce much light, and that any light that it did produce would be in the radio part of the spectrum. These kinds of things are what are known as the WIM, or warm-hot intergalactic medium. And by the way, we're going to have a bunch of really kind of fun acronyms when it comes to this stuff, because that's what you got to do now to be cool in astronomy and science, is come up with sort of cool acronyms. So this first one is called the WIM. Now, another option would be to say that there are more massive objects. When star formation takes place, there could be a lot of clumps of matter that never get big enough to, undergo fusion in their cores and become stars. And so there'd be these big cold lumps of things that might look a lot like Jupiter. And of course, there are planets around almost every star. We have a pretty good idea of that now. And there'd also be planets around those big lumpy things too that actually aren't putting off light. So we think that probably account for some of the missing matter. And then another sort of thing would be the stellar death products, things like black holes and neutron stars and white dwarf cores that have cooled off and gone dark over the course of millions and millions of years. All of this other kind of stuff is usually lumped into a group of things called MACHOs. Remember, I said there'd be great acronyms here. And that stands for Massive Compact Halo Objects. Now, if this is the kind of thing that's going on, you'd have to have an awful lot of these sort of things around. And so you think they'd be detectable if you looked carefully with really advanced instruments, such as high-altitude telescopes and space-based observatories like the Hubble and Chandrasekhar telescopes. When we do this, we do find that there is ionized forms of matter, and that's actually quite a bit of stuff. In fact, there's about 6 or 7 times as much mass in that kind of stuff than what we see in stars. And then we can use things like gravitational microlensing to look for machos on the size of white dwarfs and up. And then we can also sort of look at stars and see if stuff transits in front of them to find planets. When we do this, we find that there's only about 50% of the matter we see in stars in those macho kinds of objects. So if you add all of that together, what you find is that in all of those kinds of things, stars, WIMs, and machos, you only find about between 13 and 18% of the matter that we detect gravitationally that you can really account for. And by the way, we have a name for all of this stuff because it's made of, neutrons and protons and those kinds of things. We call that baryonic matter. Now, another way to approximate this is to run simulations of how the Big Bang would have gone to produce the elemental abundances we have observed in the early universe. You do this by looking at the ratio of deuterium to hydrogen and also to a couple of other elements to hydrogen, and then making counts of how much matter we observe compared to the cosmic microwave background radiation. When you go through doing all of that, what you come out with is the same sort of number. You get that about 16% of all the matter we seem to detect gravitationally is actually baryonic. The rest is stuff that we can't see. So it's great that we've got a much better idea of what's out there in terms of baryonic matter based on our surveys, but it really doesn't get us anywhere close to solving the problem. We still only have about 1/6 the mass of what we observe out there gravitationally. That's up from the 2% that Zwicky saw, but we're still not close. Okay, so what about gravity? Do we actually have that right? One proposed idea to fix the gravity or galaxy rotation problem, as it came to be known, was to put forward a slight modification of Newton's universal law of gravitation by adding a small, non-zero term to the acceleration that description of gravity created. This change would be so small that it wouldn't really be noticeable on the scale of solar system motions, but when one got to the galaxy and galaxy cluster scale of things, it would add that same small acceleration to every motion involving a galaxy or galaxies and kind of see to maybe resolve the problem. Now, this was first proposed by Moti Milgram in 1980, and it was called Modified Newtonian Dynamics, or a MOND approach, and it sort of was suggested as a starting place for additional work that could be done, a bit like what Alan Guth did in our last episode. Now, let's take a moment to consider the soundness of this idea before proceeding to what evidence might exist to either support or refute it. If we say that there's about 80% of the matter in the universe that's made up of stuff we have no idea about, that's a pretty bold claim. And it actually turns out that it's a much, much smaller step to say that, all we have to do is make a small tweak to our description of gravity, and, that will be responsible for what the observations made by Zwicky and Rubin are telling us. And so, that's maybe a better way to go if you actually think about it. It's either, okay, we've got gravity a little bit wrong, or 80% of everything in the universe is something we don't know anything about. Well, you might tend to go for that gravity modification. Especially, as we said, this was the approach that had been used successfully before with the determination of the Mercury or the orbit of Mercury that led to the theory of general relativity. So, how's this approach actually fared? Well, not that great. It turns out, just as had been the case in the past, reworking gravitation so that it explains all of the observations is really, really a tough thing to do. As some people might say, it's a big ask. If you make too big of an adjustment, well, you start not being able to reproduce the motions on a solar system scale, and your predictions of what should be observed are really, really off from what is actually observed. On the other end, if you lowball the acceleration estimate, then you don't get the solution to the rotation problem you're hoping for without, adding dark matter. What's even harder to do is that when you modify Newton's law, you then have to go back and modify general relativity so that that's self-consistent with your new version of Newton's law. When you try to do that, you get a version that definitely doesn't make the right predictions. Now, modifications of this approach, and remember we said when this was first proposed, it was just a starting place. So, Milgram has kind of expected that everybody would really work on this to try to modify it. So, modifications of this approach have included adding a small sort of additional field to the gravitational field, another kind of a field. And I know that's kind of confusing, we're adding a field to a field. But it turns out these aren't really as successful as explaining things, as the assumption of there actually being dark matter has been. As we'll discuss, there are a number of observations having to do with the cosmic microwave background radiation and gravitational lensing that these modified gravities just don't get right. Finally, in 2006, one of the best indirect tests yet conceived provided the strongest evidence that dark matter must actually be real. Before we get to that, however, we'll need to say a little bit more about the ideas for dark matter itself. So, in the end, while this approach hasn't actually been disproven or shown to be wrong, It really has a long ways to go before it becomes a viable alternative to dark matter, even though we kind of think that it would be a whole lot easier if we could go that route. So finally, this leads us to that third alternative. And that alternative is that there's a different type of matter that's very, very different from anything we encounter anywhere else in the universe. And for me, this is kind of like the ultimate test of our lighthouse bias. In other words, we're surrounded by all this matter that's made up of, the stuff that we see in the standard model. And so, we see protons and neutrons and electrons, and those things make up atoms, and everywhere we go and every time we interact with things, that's the kind of matter we look at. And as we're surrounded by all this matter, it has to obey certain kinds of rules in terms of how it interacts with other kinds of matter. So some examples of that are, if matter has charge, or is made up of stuff that has charge, it couples with the electromagnetic interaction and thus interacts with light. If it has certain other properties, things like isospin, it interacts with the weak force and will undergo change from one type of matter to another, what we often observe as radioactive decay. If it has a property physicists have called color, it interacts via the strong force and is made up of quarks and gluons. Thus, when we go looking for matter, we go looking for stuff that does one or more of those kinds of things. But what if there's a type of matter that doesn't have any of those properties? How would we see it except through the warping of space-time, i.e. as gravitational attraction or gravitational influence? Well, that's going to be really, really hard to do. Hence, it's the ultimate lighthouse bias or lighthouse fallacy. If we could just figure out a way to detect the stuff directly, that would be great because then we can just go out there and look for it. But the problem is that everything we know how to work with is made up of stuff that's very different than any dark matter candidate will be. In other words, any kind of instrument we're going to build, well, that's going to be made out of the type of matter we're used to, and we already know that that doesn't interact very well with these dark matter kinds of things. Okay? All we really know about the particle or class of particles is really what it can't do. It can't interact with other matter via the electromagnetic or strong force because we would have already seen that. It has to be pretty cold, meaning that either it has a very, very small rest mass, something probably less than 2% of the electron, or whatever process that creates it does so in such a way that when the particles are created, they don't have a whole lot of velocity. Because if they did, well, then we would be able to sort of detect that velocity's influence on the regular matter around it. Again, if either of these parameters were higher, we'd see it in the structure of the universe. Also, it doesn't seem to be able to clump together the way regular matter does. If it did, we'd probably see large accumulations of it that would either gravitationally affect other objects on a small scale, something like seeing a star orbiting around another large invisible mass maybe, or, it would have some other interaction like that. So this means that any type of interaction it might experience would have to have a really small, what we call a cross-section, to use the terminology of the atomic physicist. What this means is that its chance of interaction with another dark matter particle has got to be really, really small. However, with all of the stuff that it doesn't have, we do know that it must have some kind of mass, even if that mass is really tiny, for it to be able to interact with other matter gravitationally. So this leaves us with sort of two possible candidates. One of these candidates is some kind of particle that was created during the Big Bang along with all of the other kinds of things that we see. So if this is the case, it would have to be a long-term stable thing, and it would have to have been created early and then stopped being created after a certain point as the universe cooled down. These kinds of particles are generally known as weakly interacting massive particles, or WIMPs. Now, there have been a whole lot of experiments that have looked for these by trying to see, recoil in nuclear reactions or missing energy in terms of high energy sorts of environments. And while there have been a few intriguing results, none of them have been reproduced at a level that engenders any sort of confidence in them. And this is always one of the big interesting things about particle physics, is just how sure you have to be that you're detecting something, and none of the results have come anywhere close to that. Now, the other kind of particle has almost all of the same properties, but the difference here is that it actually isn't born in the Big Bang. Instead, it's the product of some sort of transition that happens at some later point in the universe's history as the cooling process after that very early period progresses. One of the things we know is that when you create an environment with enough energy, the electromagnetic and weak interactions unify, and the bosons that mediate those interactions become identical. This means that when you go from a hotter state down to a cooler state, when I talk about hotter state, I mean really a lot hotter, like hot enough that, we can only achieve these sorts of environments at places like the Large Hadron Collider at CERN. But when you go from a hotter state to a cooler state, that unified interaction breaks into two separate ones. One we call electromagnetism and the other one we call weak. And that's something known as broken symmetry. And when that occurs, new types of particles are created. In this case, photons for the electromagnetic interactions and W and Z particles for the weak interaction. So the idea here is that at some point after the electroweak force sort of splits up, there's another symmetry that gets broken, something known as a Pesce-Quinn symmetry, that would give rise to a whole new particle that's been dubbed an axion. The math that's been done for this suggests that the axion would meet all of the requirements of a dark matter particle, and it would interact very, very weakly with photons if there's a very, very large electromagnetic field. A number of experiments have been devised to detect these, and I got to tell you, I spent about a year of graduate school working with a group at the University of Florida to see if we could detect axion coupling with a strong magnetic field. Unfortunately, all I learned from the whole experience was that I'm a terrible experimental particle physicist and that the Pauli effect is really, really strong in me. And as a result of that, I soon turned to computational astrophysics, as I mentioned in the introduction to this episode. So at this point, we have no detection of the particle, and this brings us to an interesting place in the philosophy of science that we've actually discussed in a number of previous episodes. And that's sort of the matter of what's sometimes known as scientific realism versus instrumentalism. And I know I've mentioned this before, but this is just such a wonderful place to talk about this that I just can't let it pass by. For those of you who may not have listened to those earlier episodes, what scientific realism says is that when a scientist puts forward a theory to explain a set of observations, all of the elements of that theory are thought to be real. An instrumentalist, on the other hand, says that only those things that have been observed are actually real. Anything else that hasn't been observed that's a part of your theory is just an instrument that's been created to explain those observations. So let's give an example of this, maybe from chemistry, that will help sort of understand that. Let's think maybe we're trying to sort of explain some sort of a process of a chemical reaction that occurs. Let's say that when you pour two different solutions made of two different chemical substances that have been dissolved in water, as you pour those two solutions together, what you see is that a bright yellow precipitate is formed, and that precipitate sort of settles to the bottom of the container. When you test the precipitate, you find that by observation, it's made of a combination of two of the chemicals that you had from in each of the solutions. In other words, one from one solution and maybe one from the other solution. And it seems like those two individual elements have combined to form a new substance. Now, how do you explain this? Well, let's say you try to explain this using a description of chemical bonding that involves the existence of ions that create a covalent bond through the sharing of electrons in valence shells of atoms, and that combination is now non-soluble because it isn't broken apart by the ionic nature or the polar nature of the water molecules, and thus it settles out in solution. And I know that all sounds like an awful lot of stuff, and if you didn't follow the chemistry, don't worry about that so much right now. Now, if you are a scientific realist, you're going to say, oh, that sounds really great. But the instrumentalist is going to point out that you're really assuming a lot of things that you've never seen. Things like atoms and electrons and electrochemical bonds and a whole bunch of other stuff. What the instrumentalist is going to say is that your description is fine, but that you don't know if any of those things really exist because you haven't observed them. So Dark matter is a great example of an instrument in this sense. What we do is we start with some observations of the motions of astronomical objects that we can't explain. Zwicky invents a new type of matter to explain the observation, and Rubin's work really sort of resurrects that idea. Since then, a bunch of scientists have assumed that there is dark matter, but there's no actual detection or observation of the stuff itself. Thus, dark matter is an instrument to explain how nature behaves, but it may or may not be real. At least that's how the hardcore instrumentalist will see it. The difficulty with this approach is that it ignores continuous overwhelming success when the instruments are used to explain a broad array of observations. If we go back to our chemistry example, what we can see if we broaden our research a bit is that things like atoms, electrons, chemical bonds, all of that explain a whole lot more than just one observation, and even all of the sort of similar types of observation. Atomic theory has been really successful at explaining things as diverse as gas laws and chemical reactions and radioactive decay and a number of other phenomena. Electrons can account for electric current and chemical bonding, electromagnetic waves, the creation of photons of light, all kinds of things. Even if we had never observed those actual things like electrons and atoms, it's really hard not to think that atoms and electrons aren't real because they explain so many things. What this is, in other words, is a complex inference from best explanation type of argument. Not only are atoms and electrons the best explanation for the chemical reaction process, but there's a whole lot of other things it explains really well in addition to that. And so the probability of those things actually existing is thought to be very, very, very high. So the question comes up then, can we do the same thing for dark matter? It turns out that if we're going to move the dark matter hypothesis to the head of the line, we really have to do that same kind of thing. We have to find more than just one thing. If we just look at the galactic rotation problem, dark matter is one explanation, but it's not the only one. And it may not even be the best one, as some of the Mond versions actually work just as well. The same is true for Zwicky's cluster observations. Now, putting the two together does make for a stronger case, but that's still probably not enough. What we need are lots of different things, just like we have with atoms and electrons. So let's talk a little bit about some of the other evidence that we can accumulate. One of the strongest pieces of evidence has to do with simulations of galaxy cluster collisions. So, as we've stated, galaxies are found in clusters of several members, and every so often, in a universe filled with something like 10 to the 24 galaxy clusters, and that's a 1 followed by 24 zeros, that's the number of clusters. Each cluster has hundreds of members. We're bound to come across two clusters that are running into each other. Now, due to the vast distances separating the individual galaxies, this collision, at least in terms of the galaxies and the stars that make them up, are a bit like firing two shotguns that are pointed at each other. Since each of the shotgun shells is filled with a few dozen pellets, when they're fired, the pellet clouds, if I can use that, when the guns are fired, they're going to fly towards each other. But since each of the individual pellets is separated by a distance that's much larger than the size of the pellet itself, the chances of a pellet-pellet collision are actually pretty small. What that means is that the pellets are just going to pass right on through each other, continuing to travel on the trajectories determined by their velocity. However, there's actually another part of this, and that is whenever you fire a gun, you sort of get gases and smoke that come out of the end as well. So if we think of firing our shotguns and we have our shotgun pellets coming out of the end of the gun, that's going to be accompanied with a bunch of gas and smoke that's ejected with those pellets. And that gas and smoke, when it interacts with the gas and smoke from the other gun, is actually going to act in a very, very different way. So what's going to happen is those clouds of gas, when they interact, they're going to slow down, they're going to collide with each other, and it's going to change the motion of the objects in a way that you don't see with the pellets. So let's see if we can apply this analogy to our colliding clusters. First, the galaxies are going to be just like the pellets. Second, the intergalactic gas and dust. Remember that stuff that we talked about, the ionizing particles, all of those things. That's going to act a lot more like the smoke from the shotguns that have been fired. What's interesting about this is that when the two distributions of gas on these colliding galaxy clusters interact, they're going to do two things. First is that they're going to slow down and lag behind the clusters as they impact the other material from the other cluster. The other is that when they sort of impact and they compress, they're going to heat up and they're going to give off light. And it turns out the way they give off that light is going to be in the ultraviolet and X-ray parts of the spectrum. And this is great because you can actually observe that. Now finally, if there's dark matter present in those galaxy clusters, and that's sort of what Zwicky thought there was going to be, is there's a whole bunch of dark matter sort of filling in all that space around those galaxy clusters. Since it doesn't interact with other dark matter via the normal mechanisms, it should actually act, even if it sort of feels like it's spread out like the gas and dust is, it's going to act a lot more like the galaxies in that it's going to pass through the dark matter of the other cluster. Now, here's where things start to get really interesting. In 2006, we found a colliding galaxy cluster with the eminently memorable name of 1E0657-558, or as it got renamed in a much more, easy way, just called the bullet cluster. And what it turns out is that the bullet cluster was actually made of two clusters that were in the process of colliding at relatively high speeds. When we observed this cluster, we saw exactly what we would have expected to see in terms of the light. The light from the galaxies showed that the galaxies were passing through each other, weren't a whole lot of collisions going on there, just like the pellets from the shotgun. When we observed the cluster in X-rays, the cluster showed exactly the lagging X-ray signature we would have expected from the gas and dust that would have surrounded the cluster. And that's fantastic. The key piece of evidence, however, had to do with how the mass distribution of the cluster gravitationally lensed the stuff that was even further away. Now, to get this, you sort of have to remember a couple of pieces of things that we've already talked about and sort of pull this all together. First thing to remember is that in the observations that we have, we know that there's about 6 or 7 times more diffuse material than there is stuff associated with the galaxies, the stars and black holes and all of that stuff. So, there's about 6 times more material with the stuff associated with the observations of the X-rays, which are lagging behind, than the matter in the stars and the sort of, like you say, the mass of halo objects in the galaxies. So, if there's no dark matter, the lensing that the galaxy does should center around where the gas actually is. If there is dark matter, though, and that dark matter travels with the galaxies because it doesn't interact with the other dark matter, then the gravitational lensing will center around the galaxies and have a much, much stronger signature than it would around the gas. As you may have already sort of sussed out, what we observe is the latter. There's a lot more mass in the galaxies than there is in the diffuse intergalactic material, and most of that is matter that we just don't see. Now, while this is probably the cleanest and just most clever way of sort of differentiating between this and showing that dark matter really does seem to exist, there is other evidence that can be derived in different ways as well. You can actually sort of look at the mass in other galaxies and see what's going on. You can look at the structure of the variations of the cosmic microwave background radiation. And finally, you can look at the distribution of matter across the universe. This last piece of evidence is especially compelling. In this approach, matter tends to clump up in certain ways due to both its own gravitational interactions and also due to the pressure exerted by photons, especially during the period of time when the early universe, when the density of photons was so much higher than it is now. When simulations are done as to what the universe should look like based on these competing forces, what's found is that there shouldn't be a whole lot of what we call small structure in the universe. In other words, a way to sort of think of that is a small group of galaxies, like our own local group, really shouldn't exist. All you should do is get really big clumps of clusters and not a lot of small filamentary sort of structures in the universe. However, if dark matter is added early on, what we find is that structures on the scale that we see with our local group occur naturally due to the added gravitational effect of all that extra mass. And in fact, one of the really interesting things that has been done is to simulate how the universe evolves from the Big Bang in a number of different scenarios. You run different simulations all the way from there not being any dark matter to having the amount of dark matter the observations that we're making nowadays seem to suggest. And what we find when we do that is that none of the simulations match what we actually observe in the cosmos until we put in about the same amount of dark matter that we actually think that there is actually there. Now, in terms of the comparison of these observations with the MOND, or modified gravitational models, what we see is that the modification of gravity doesn't give predictions that are consistent with what we see. We don't get the same variations in the cosmic microwave background radiation. We don't get the same sort of structures in the way the universe sort of evolves from those early states to what we see now. Hence, because of that, it becomes clear that dark matter supplies the best explanation for a whole variety of different observations. So why don't we just come out and say that dark matter exists? Well, the instrumentalist ethos runs pretty strong in a lot of scientists these days as a result of the work, at least early on, by Heisenberg and Pauli on quantum mechanics way back in the 1920s and 30s. And this carries forward especially into particle physicists today. One of the things that these folks will point out is that we know that our present standard model of particle physics is incomplete in a variety of ways. This leads many of these physicists to believe that there will be another revolution in physics wherein we will develop a whole new way of looking at nature, and in this we may well, rewrite our understanding of gravitation completely. In other words, they haven't thrown out the MOND idea yet, though, as they will all freely admit, we would be looking at something much more radical than the minor tweak to what presently exists that most of those models presently suggest. Such speculations are, of course, the purview of the most cutting-edge research, and so a bit beyond the scope of a historical podcast such as this. Additionally, it turns out that matter isn't the only thing that's dark and mysterious. To close this episode, I'd like to take a few more minutes to talk about Vera Rubin and her contributions not only to astronomical research, but also to the culture of science both in the United States and internationally. Dr. Rubin was one of the best observational astronomers of her generation. Her collaboration with Ken Ford resulted in equipment and methods that allowed astronomers to not only observe galaxies in bulk, but also to look deep into them and measure the motions and compositions of individual parts of those galaxies. Her work with Jeffrey and Margaret Burbidge was not only foundational to understanding galactic structure and morphology, but also just truly epic in terms of observing effort. As a graduate student, talking to some of the old-timers around the department, I heard stories of the observing runs at Palomar that involved gathering light from faint galaxies or individual molecular clouds within those galaxies that lasted not just hours, but days. Of personal interest to me, among the last of the big projects she undertook, once again hoping to step out of the spotlight, was the observation of a certain type of galaxy that has some of the characteristics of spiral galaxies and some of the characteristics of what are known as elliptical galaxies, and they're known by their designation as S-type galaxies. When she made careful observations of these systems, what she found was again paradigm shifting. Dr. Rubin observed that a significant portion of the stars in these galaxies rotated in the opposite direction than that of the rest of the stars. These observations, made in the early 1990s, provided some of the first really hard evidence for what was going on with galaxy mergers and the fact that certain types of galaxies were the products of those mergers rather than some other process. And this is a process actually seen throughout the universe and is thought now to be responsible for the barred structure seen in as many as 2/3 of all spiral galaxies, including our own. As I've mentioned, it was these observations that formed the foundation of my program of numerical simulations of galactic dynamics that resulted in my PhD. One of my biggest professional regrets is that I didn't get a chance to meet Dr. Rubin and let her know how important her work was in my career. Additionally, Dr. Rubin was a strong advocate for women in science at a time when there were still just a huge number of barriers to entry and acceptance of women researchers in the physical sciences. She was only the second woman astronomer elected to the National Academy of Science, and only the second woman to receive a gold medal from the Royal Astronomical Society, the other, of course, being Caroline Herschel. I've met with a number of female colleagues who list Dr. Rubin as one of their primary inspirations for going into the field, and she was known as a mentor to many. She advocated for greater inclusion of women scientists in national scientific organizations, on policy committees, and on review panels. And while she expressed frustration with the slow pace of change, her voice for greater inclusion was a primary motivator in creating opportunities for female scientists all across America. With all this in mind, allow me to dedicate this episode to her memory and all of the work that she did for so many around her. As we wrap up this episode, this week's other shout out goes to the men and women of Ball Aerospace, United Launch Alliance, NASA, NOAA, and all of their partners. Late last Saturday night, the JPSS-1 weather satellite was successfully launched from Vandenberg Air Force Base atop a ULA Delta II rocket. The vehicle is in orbit, its solar array has deployed successfully, and all of the instruments are getting power. Over the course of the next few months, all of the onboard systems will undergo testing and calibration before the vehicle is designated NOAA 20 and becomes fully operational. And once this happens, will be added to the growing fleet of weather satellites that gather information about the Earth's atmosphere that affect forecasting models, as well as a number of other scientific missions as we continue to gain a better understanding of this thin cocoon of gas that sustains us. As we discussed in our unscripted episode on the JPSS program, this orbiter promises to achieve a quantum leap in our data-taking capability with respect to what we can learn about the Earth's atmosphere. As an example, it should be able to measure the temperature of the atmosphere at almost every altitude from the surface upwards to within 0.1 degrees Kelvin. I hope that everyone involved in the planning, construction, and launch of the satellite has taken a bit of time to celebrate. Here at the Scientific Odyssey, we raise a glass to your efforts. You all have done something truly amazing. If you'd like to listen to that earlier JPSS episode, or any other topic we've covered, you can subscribe to the show at all of the usual places: Apple Podcasts, Google Play Music, Stitcher, iHeartRadio, TuneIn FM, etc. You can also join the crew by liking our Facebook page or by following me on Twitter @ChadDavies. It's Thanksgiving week here in the United States, so let me say thanks to all of you who take the time to join us on this voyage of discovery. Every time I think of the reality that I get to share my ideas and thoughts about science and how it's done and how it's been done with you all, I'm just blown away by the fact that you're here with me. It's what an amazing world we live in, where I can share this voyage with all of you through the technologies of both audio recording and the internet. I hope that you'll take a moment to revel in all of the geeky coolness that is. Next week, we'll try to bring this part of our journey to a close by looking at the last piece of the model and reflecting back on where we've been. Until then, full sails on your journey.